Hello everyone, in this video we're going to look at section 12.2 and we're going to pick up where we left off. We were looking at this example 3 where we had r and u and we wanted to find the derivatives. So in this case we wanted to find the derivative of u cross u prime, and so in order to do that we're actually going to use property 5 here. Alright, so in this case the derivative of u cross u prime, x doesn't need cross u prime by the formula is equal to, we leave the first one alone, so u of t cross, and then take the derivative of the second, so that's the derivative of the derivatives, that's u double prime of t, plus, now we take the derivative of the first one, which is u prime of t, and then leave the second one alone, which is u prime of t. And so this right here, remember any vector cross product with itself, right? This is u, in this case, and vector valued functions, it's the same way. Anything cross product with itself is equal to 0, right? Because that's the derivative cross the derivative. So that's why in this case, this formula makes life a little bit easier. So we need u of t and then cross u double prime of t. So we should probably find u double prime of t, right? So u of t is given right up here. So let's find u prime of t. So u prime of t is going to be 2ti minus 2j plus 0k. So that means that u double prime of t is the derivative of that. So that's 2i minus 0j plus 0k, right? Once again, that's a lot of zeros, right? So this cross product is going to be relatively easy. So when I plug in, I get I, j, and k for my cross product. I would get t squared, because I'm putting u in, so t squared minus 2t and 1, and then when I put u double prime in the second or in the third row, I would get 2, 0, and 0. Right, so there's a lot of zeros there, so this cross product will be relatively easy to do. So in this case, I get negative 2t1, 0, 0, I minus t squared 1, 2, 0, j plus t squared negative 2t, 2, and 0, k. And so when I do this first determinant, I get 0. So this is 0i minus, when I do the second determinant, I get negative 2, right? J. And then when I do the third one, I end up getting minus negative, so plus 4t. Okay. All right, so this one ends up being 2j plus 4t. K, another vector valued function, as we expected, because the cross product of two vector valued functions is a vector value function. So just as before, remember this was a formula, right? So I could also find this derivative by first computing the dot product or the cross product there, and then finding the derivative of that. So let's do it that way to make sure we can get the same answer. So alternatively, let's find u of t cross u prime of t first. So if I did that, scooch this down a little bit, I end up getting I, j, k, and I plug in u, which is t squared, negative 2t, and 1, and then now I'm plugging in the derivative, right? So u prime of t, so I get 2t, negative 2, and 0. So when I compute this cross product, maybe give myself a little bit more room here, I end up getting negative 2t1, negative 2, 0, I minus t squared 1, 2t, 0, j plus t squared minus 2t, 2t minus 2, k. So in this case, I get positive 2 because it's minus negative, so 2i minus, and in this case it's minus 2t, so minus, so 2 minuses, this gives me positive 2t here, and j, and then plus I get negative 2t squared minus negative, so plus 4t squared k. So that gives me 2i plus 2tj plus 2t squared k. All right. Now I can take the derivative of that. So the derivative of u of t cross the derivative of u is the derivative of what we just found, right, which is 2i plus 2tj plus 2t squared k, which when we compute the component, when we compute the derivative, we do it component-wise. So I get 0i plus 2j plus 4tk, which is 2j plus 4tk. And notice that's the exact same answer we got as before. However, the cross product in this case was maybe a little bit more complicated than the cross product above when we did the formula. So maybe in this case, the formula is easier. Okay, so how about integration? So integration will be just as before with the derivative, and it's just we just take the integral of each piece. So if I want to find the antiderivative of r of t, then I take the antiderivative of each piece. In the case where I have a definite integral, then once again I just take the definite integral of each piece. And this can be extended to vector value functions of 3 dimensions. I just take the antiderivative of all 3. One really important difference, though, is that the constant of integration, right? When I took integrals of real valued functions, the constant of integration was just a scalar, right? It was just some number. Now, the constant of integration is a vector constant. So it's a vector, no longer just a scalar, right? So that's really the difference here. So when I do plus c, I should do plus like a bold c, or plus a c with a little line over to make sure it's a vector, right? So in this first example, if I want to take the integral of ti plus 3j dt, I could rewrite this as the integral of ti dt and then plus the j1, but we can just kind of skip writing all that. If I take the antiderivative of the first one, I would get t squared over 2 and then I, plus now the antiderivative of 3 is 3t j, and now instead of plus c, we do plus c, but we put a little vector symbol over top of it to show that it's a vector, right? So that one, we really don't have to write out this whole like formula here. We can just kind of do component by component in our head. In the next one, though, since it's going to be a definite integral, I think it will be helpful, and the way we'll do it is to actually write out each one individually, just like that. Okay, so if I want to evaluate this guy, so the integral from 0 to 1 of, I'll write that as t to the 1/3 since it's the cube root I, plus 1 over t plus 1j, plus e to the negative tk dt. Well, I could rewrite that as the integral from 0 to 1 of t to the 1/3 dt I, plus the integral from 0 to 1 of 1 over t plus 1 dt j, plus the integral from 0 to 1 e to the negative t dt k. So basically, I just distributed the integral to each component. Now I take the antiderivative. So 1/3 add 1 is 4/3, so I get 3/4 t to the 4/3, and I'm evaluating that from 0 to 1, and then I'm multiplying it times I. And then here, the derivative of 1 over t plus 1 is ln of the absolute value of t plus 1, the integral, and evaluated from 0 to 1 times j, plus this is negative e to the negative t, evaluated from 0 to 1, multiply that times k. So then I do this evaluation, I end up getting 3/4 minus 0 times I, plus ln of 2 minus ln of 1 times j plus negative e to the negative 1 minus negative, so plus e to the 0. Okay. And we can simplify this. Ln of 1 is equal to 0. E to the 0 is equal to 1. So if I simplified that, I'd end up getting 3/4 I plus ln of 2 j plus, and now I'm going to switch things around. So I write this 1 minus, and then e to the negative 1 is 1 over e. So 1 minus 1 over e times k. And that's my final answer there. And notice that I don't have a plus c because this is a definite integral, right? The same reason I don't have a plus c in the real valued function case. Okay, so how about an initial value problem? So let's find the antiderivative of r prime of t that satisfies the initial condition r of 0 equals to that. So we did similar problems like this probably when you're in Calc 1. So basically the idea is we take the antiderivative of this guy to get a function r of t plus some constant, and then we're going to use this initial condition to find that c. Right, that's kind of the idea here. Okay, so in general, if I wanted to find r of t given the derivative, which is what we're given, I take the integral of r prime of t, right? That's the fundamental theorem of calculus, is that the antiderivative of the derivative is the function. So I'm going to take the integral of the derivative, which is given by the problem, that's cosine of 2t I minus 2 sine of tj plus 1 over 1 plus t squared times k dt. And in this case, I'm also going to do what we did like in the last problem where I distribute it, because when I take the antiderivative of each one of these pieces, because when I'm taking the antiderivative is a real valued function, each piece, each component will have its own plus c. And so that's why it's going to be easier to keep track of if I distribute the integral to each piece. So for instance, here I get the integral of cosine of 2t dt times I plus the integral of negative 2 sine of t dt j plus the integral of 1 over 1 plus t squared dt k. And I guess maybe I should say the reason why we end up getting a vector, a constant vector, is because of this property, right? When I do, if I look back here, when I'm doing, say if I look at this formula for taking the derivative, or the antiderivative. So when I take the antiderivative of f of t, I would get the antiderivative of f of t, say with big F of t, plus some constant times I. And then here I get the antiderivative of g, so maybe big G of t, plus some constant in the j spot. So I end up getting big F of t times I plus big G of t times j plus the constant, the first constant, maybe we'll call it C1 I plus C2 j. Right? And that's why this is called just some constant vector, but really it has constants in each component. So that's why we're kind of skipping that step where each little piece, when we take the antiderivative, has its own constant, which is why it's a constant vector. Right? And so that's what we're showing in this example, is that in order to solve this initial value problem, we need each one of these individual pieces to have their own constant. So when I take the antiderivative of this, I get 1/2 sine of 2t plus a constant, right? Because when I take the antiderivative of this is a real valued function, so I need the plus c, I, plus the antiderivative of sine is negative cosine, so two negatives make a positive, so I get 2 cosine of t plus a constant there in the j, plus, and now the antiderivative of this is tangent inverse of t plus a third constant times k. And now is where we use the initial condition in order to find what C1, C2, and C3 are. In other words, to find what that vector constant is. So what we do here is we're going to plug in t equals to 0, right? So this must satisfy our initial condition, right? So letting t equals to 0, right? Because that's what this initial condition says. So we plug in t equals to 0. We get r of 0. So we're plugging in 0 into our function and seeing what we get. And then we can set each one of our pieces equal to 3, -2, and 1. Right? So I get r of 0 is equal to 1/2 sine of 0 is going to be 0. So I just get C1. I'm right, 0 plus C1 I plus cosine at 0 is 1. So I get 2 plus C2 J plus tangent inverse is going to give me 0 plus C3 K. And remember, we need each one of these components to be equal to the blue function, right? So if I were going to do this, maybe, so I'd have, so we'll say this blue has to be equal to this constant, this green has to be equal to this constant, and this purple has to be equal to this constant, right? So in other words, what do we end up getting? C1 has to be equal to 3. C2 has to be equal to -4. So that way when I add 2, it gives me -2. And C3 has to be equal to 1. Right? So therefore, our vector valued function, r of t, that we found that satisfies that initial condition is 1/2 sine of 2t plus C1, which is 3i, plus 2 cosine of t plus C2, which we found to be 4, so -4j, plus tangent inverse of t, and then plus C3, which is 1, so plus 1 times k. And now that is our vector valued function, r of t. Another way we could think about this is, remember, it was our antiderivative plus c, right? So this could be like 1/2 sine of 2ti plus 2 cosine of tj plus tangent inverse of tk plus now all the individual pieces, right? 3i, right? These are two different things. So plus 3i minus 4j plus k, right? So this, in other words, is my c vector. That's my constant of integration. But it makes sense to rewrite it integration. But it makes sense to write it like this, that I boxed off, better than it looks to write it in the bottom. But just for our understanding, I figured that's kind of nice to write out. All right, that's all I have for this video. Thank you.